Thank you. My name is George Xu. On behalf of my coworkers, we are very happy for the opportunity to present our work on ARCHER through this pre-recorded video. ARCHER is a Monte Carlo code designed for multi-particle radiotherapy through the use of GPU-accelerated simulations and deep learning-based denoising. In radiotherapy, the process begins with obtaining patient CT images, which is followed by contouring of tumor targets and organs at risk, which then is followed by dose calculations and treatment plan optimization, which normally are very time consuming. Finally, the treatment plan is delivered to patient. Therefore, the dose calculations in radiotherapy must be accurate and fast. In radiotherapy community, Monte Carlo particle transport method is considered the gold standard. However, there are many modern clinical procedures that require Monte Carlo dose calculations to be further shortened. Potential ways to speed up Monte Carlo calculations includes, of course, simplification of physics, GPU-based parallelization, deep learning-based denoising. Our presentation will be talk about these three aspects. The ARCHER project began in 2009 under the initial plan to design a testbed for emerging hardware such as GPUs and many integrated cores. MIC has since become obsolete. The project launched at Rensselaer Polytechnic Institute in Troy, New York, United States. And then the project moved with me to China at University of Science and Technology of China in Hefei. The project has graduated so far 9 PhD dissertations and published more than 50 journal papers. The project finally concentrates on GPU parallelizations as well as radiotherapy applications. Since 2014, we proposed the concept of real-time Monte Carlo simulations. Since 2019, we proposed Monte Carlo denoising. In this animation on the right, it was the first time to illustrate the concept of real-time Monte Carlo through a simple shielding design cases, where a user can drag and change the shielding design while interactively displaying the dose calculation result without visual delay. So what is real-time Monte Carlo calculations? Well, in computer science, real-time computing refers to hardware and software systems that are subject to a real-time constraint. The tolerable limits for latency in real-time video processing is about 20 milliseconds, while in real-time telecommunications, such as using cellular phones, a delay in less than 300 milliseconds are considered to be acceptable. So in 2014, we proposed a time constraint of 500 milliseconds or half a second for real-time Monte Carlo radiation transport simulations. Perhaps a latency of half a second or even less would allow us to perform interactive data analysis for radiation shielding design, for cancer treatment plan verification, and for radiotherapy replanning. So the question becomes, real-time Monte Carlo of 0.5 seconds is feasible. Of course, we're going to have to simplify the radiological physics. For example, in the code that we use for protons and carbon ion simulations, we adapted very detailed physics models from giant full codes. And previously, we have simulated photon radiotherapy for a machine called tomotherapy. So in this paper published in 2014, we compared ARCHER results with those from giant forecoat. So in this image here, you are looking at a two-dimensional dose map from ARCHER and compare that with those from giant 4. Visually, the dose maps agree with each other very, very well. In terms of computing time, ARCHER took 6 seconds to come up with those distributions when using giant 4. It took 500 CPU hours. Previously, we also performed a study for a procedure called VMAT for treating prostate cancer. In this paper that was published in 2020, we compared results from ARCHER with those from EGS NRC. As you can see from the two-dimensional dose maps, the results agree with each other very, very well. In terms of dose volume histogram, the results also agree with each other closely. If you look at the computing performance, ARCHER used one GPU card, took 48 seconds to come up with those dose distributions, whereas EGS NRC took 120 node cluster CPUs and 24 hours to come up with the same dose result. Of course, for radiotherapy dose calculations, we have to perform detailed calculations for what's called phase space files. The images on the right illustrates how electrons interact with constant target to produce strong photons going through primary collimators as well as secondary collimators. Now, phase space files has to be performed for every machine, and then the information is fed into ARCHER-a Monte Carlo transport calculations involving the patient. Now, of course, this result were performed by several PhD students. Now, we all know that Monte Carlo calculation suffers from noise. And this picture illustrates that more number of particles that's used, the less noise the results will contain. For example, using 10 to the 6 number of photons, this is the level of noise in the dose calculations. As the number of particles is increased to 10 to the 10th, and this is what the level of noise look like. Therefore, in 2019, we proposed the Monte Carlo denoising method using convolutional neural network that we developed called MCENet. The method basically uses a low count and high noise dose map as the input, and the neural network, after extensive training, would predict what the high count, no noise dose map would look like. As I mentioned earlier, for deep learning-based denoising method to work, the training data is very important. So far, we have utilized 615 patients who underwent photons, protons, and carbon ion therapies. Using the well-trained CNNs, the workflow of GPU-based Monte Carlo simulation plus deep learning-based denoising would include 2 steps. Of course, in the first step, we would do a dose calculation very, very quickly because we are using GPUs. However, we only simulate relatively small number of particles, so the dose map would contain certain noise. In the second step, we use that no particle number dose map into the neural network denoising model, in which you would predict a result that's equivalent to the dose calculation from a large number of particles. Of course, our objective here is to demonstrate the feasibility of real-time Monte Carlo dose calculations. Very recently, we received some very exciting results. In the next 3 slides, I will share those results with you. First, I would like to discuss the result for photon radiotherapy, in which we considered IMRT clinical procedure as well as VMAT procedures. In the case of IMRT, as you see, we use a low count as input into the CNN. We would denoise and we would produce a dose result that's equivalent of those from 10 to the 9th photons. Now, the entire process I would like to indicate took less than 0.153 seconds to complete. That includes the dose calculation to noisy information plus the deep learning-based denoising method. Altogether combined would take 0.153 seconds. This slide shows the recent result for proton dose calculations. We considered head and neck cancer and pelvis cancer treatment, and again using a low proton number as input, we produce a dose map that's equivalent of those from 10 to the 8th protons. Again, the entire dose calculation took less than 0.138 seconds to complete. In the case of carbon ion calculations, it also took less than 0.1004 seconds. However, in the case of carbon ions, we had to use multiple GPU cards to arrive at this real-time speed. We are now the only groups that are working in this Monte Carlo denoising since the concept was proposed in 2019. There are several very important publications. For example, the group from Southwest Medical Center in Dallas, United States, they investigate proton denoising using in-house the GPU software. They reported computing speed in about 0.2 seconds. A group from Cancer Hospital in Beijing, China, they studied proton radiotherapy denoising, and they reported calculation using 60 seconds. Another group, also from China, Institute of Modern Physics, they investigate carbon ion denoising. They reported calculation using the method that took 16 minutes. These two groups, number 2, number 3, they did not use GPU for the dose calculation. That is why their time for the entire process is relatively long. If you look at the latest radiotherapy method called adaptive radiotherapy or ART, the process involves many steps, including image registration, image segmentation, and Monte Carlo-based replanning, and dose verification, and so forth. Therefore, a very fast Monte Carlo-based dose calculation is extremely important. To this end, we have worked with recent technologies to develop a commercial software, which has recently received US FDA pre-market approval. And this is the interface of this software. This is the last slide of my presentation. I would like to conclude saying that real-time Monte Carlo computing has been demonstrated by us and also by other groups. Monte Carlo dose engine is and will continue to be essential in radiotherapy, particularly involving proton radiotherapy, heavy ion and helium ion radiotherapy, as well as boron neutron capture therapy. Software solutions, including deep learning-based automatical multi-organ segmentation and DL-based denoising, are available to boost clinical workflow. Since 14 years ago, we began to develop ARCHER. The software is still growing very quickly. We already added deep learning-based denoising to photons, protons, as well as carbon ions very recently, and the work progress will allow us to continue with the BNCT and helium ion applications. That concludes my presentation. Thank you very much for your attention. Bye-bye now.